Okay, well let's do a lecture on section 8.1, which is on arc length. Okay, and the method for finding the formula for the length of a curve is very similar similar to finding the area under a curve. The method essentially falls in the exact same way. So what we do here, okay, what we're going to try to do is let's say we have a curve going from A to B, and this is x and this is y, and we'll say that y is some function f of x. Okay, and what we're going to do is use the fact that we know the length of straight lines, okay, and chop up the interval AB into small partitions of width delta x. We know that as delta x gets small, f of x in an interval of width delta x essentially looks like a straight line. Okay, so that's what we're going to use, and then we're going to do some looks like a straight line. Okay, so what we're going to do, all right, so let's draw the picture again. Let's make this a little bit bigger. So you have x here, and you have y there, so we have this function that's going from A to B. Okay, now what we're going to do is we're going to chop up that interval into, in theory, equal subintervals. We're going to call A x0, and then the next point x1, dot, 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 all the way till we get to B, which we'll call xn. Okay. The length of the curve connecting the points, so two consecutive points, xi, yi, and xi plus 1, yi plus 1, is approximately equal to the square root of xi plus 1 minus xi squared, okay, plus yi plus 1 minus yi squared. Okay, that's the formula for the length of a straight line. And what we'll do is we'll call this Li, the length of the ith line approximating the curve, and then therefore we'll call the arc length, which we'll denote by L, to be L is equal to the sum I going from, in this case it'd go from 0 to n minus 1 of Li. So adding up all of these little lengths. So essentially, what are you doing? What you're going to do is take, and this is sort of fine here. Oh, that's my hand. You take that length you approximated with a line. Take that length approximated with a line, and notice all these lines are going to be different. You take that length you approximated with a line. Take that length, that length, that length. In some places you're doing a good job. In other places you're not, but as you thin out this region, so you continue to add, you thin out the regions, so you add more points, those lines become more and more like the function, and you get a better estimate for what the length of that curve is. Okay, so in this case we allow delta x to go to 0. Alright, so let's see what the implications of this is. So let's take, our L, what we're going to do is we say that L is approximately equal to the sum I going from 0 to n minus 1, okay, of Li. This is equal to the sum I going from 0 to n minus 1 of the square root of xi plus 1 minus xi squared plus yi plus 1 minus yi squared. Okay. Now, the distance between any two x points is just delta x. And in a perfect world, this would just be delta I, but we know that y doesn't change the same everywhere. It'll also be a constant function. So we're going to call this delta yi. Okay, so this is equal to the sum I going from 0 to n minus 1 of the square root of delta x squared plus delta yi squared. Now, using differentials, and the mean value theorem, we know that there is a xi star that is such that xi is less than or equal to xi star, which is less than or equal to xi plus 1, okay, and that delta yi is identically equal to f prime at that xi star times delta x, okay, which is important because now we're starting to get like terms. So we take this, we plug it in there, we get that L is approximately equal to the sum I going from 0 to n minus 1 of the square root of delta x squared plus f prime at xi star delta x quantity squared. Okay, we can factor out a delta x squared from the whole square root and get that L is approximately equal to 1 plus the derivative of f evaluated at xi star squared, factoring out the delta x from the square root, I get delta x there. Okay. Letting n go to infinity, well, this is just, if I let n go to infinity, this is just equal to the integral from a to b of the square root of 1 plus f prime at x squared dx. Okay? Awesome. So this is a good formula. Alright, so let's put down our results. So, therefore, the length of the curve y is equal to f of x if f prime is continuous is L is equal to the integral from a to b of the square root of 1 plus f prime at x squared dx if the curve runs from x is equal to a to x is equal to b. Okay. Okay, so I'm fine if all you do is remember this formula, as long as in the back of your mind you know the derivation is essentially using a bunch of straight lines, which is pretty much the derivation in any calculus argument. But I just really want you to know the formula. So let's do an example. Okay. Find the length of the curve y is equal to 3/2, and then let's say x to the 3/2 as x goes from x is equal to 0 to x is equal to 1. Okay? So the solution here is pretty straightforward. The integration might be difficult, but the setup is always pretty straightforward. So solution L is equal to the integral from 0 to 1 of the square root of 1 plus, well, here this is f, so if I take the derivative there I get what? 3/2 squared x to the 1/2, okay, and then I got to square the derivative, which will get rid of that square root, which is nice, and then I get dx. So this becomes the integral from 0 to 1 of the square root of 1 plus, and then now it'll be 3/2 to the 4th power, or what would that be? 3 to the 2nd power is 9, 3 to the 3rd power is 27, so 3 to the 4th power is 81, so you're going to get 81, and then 2 to the 4th power is 16, and then you're going to get x, because if I square the square root I just get x dx, so let u be 1 plus 81 over 16 x, then du is 81 over 16 dx. So then your integral becomes integral, if x is 0 then u is 1, if x is 1 then u is, what would this be, 97/16. Okay, and then now you're going to have u to the 1/2, okay, du, and then you got to go ahead and divide by what's in front of dx there, so 16 over 81. Okay, so anti-differentiating, this becomes 16 over 81, 2/3 u to the 3/2, and then evaluate it at 97/16 and 1. So this gives you 16 over 81, and not to skip out on the, oh, that's 2/3. Not to skip out on the algebra here, but let's just do 97/16 to the 3/2 minus 1 to the 3/2, which is just 1. And that, folks, is your final answer there. Okay, so that's the length of that curve. Okay, you could have drawn it, but you know the formula gives you everything you need. Okay, well, so thank you for listening to that, and we'll have one soon here on surface area.